Hello again. In this video, we are going to look at an application of calculus to economics. And there are a lot of applications of calculus to business and economics, but this is kind of the most famous one. It's the one you read about even in standard non-applied calculus textbooks, like Thomas's calculus, the textbook I use for the regular calculus sequence, has a little section on this. And I'm talking about marginal analysis. So let's look at a cost function. Let's say we are manufacturing and selling widgets, and X is the number of widgets manufactured, and C of X is the cost. And notice that in this application, it only makes sense to talk about X being a natural number. Because we cannot manufacture and sell half a widget, for example. And often when we do calculus, we just sort of quietly ignore restrictions like this. But here we're going to take it seriously and we're going to see where it gets us. Let's pick a number, kind of at random. Let's look at 12. So C of 12 is the cost to manufacture 12 widgets. What about C prime of 12? What about the derivative at 12? Let's tackle this using the limit definition of derivative. Let's just tackle this directly. C prime of 12 is the limit as h approaches 0 of C of 12 plus h minus C of 12 all divided by h. And the thing about this limit is that mathematically, we're letting h approach 0, but due to real-world reasons, h can't get that close to 0. Due to the restriction on the domain that the cost function only takes on the non-negative integers. Because, I mean, suppose we let, what's a number that's close to 0? 0.001 is a number close to 0. But if we ask what happens when h equals 0.001, we get C of 12.001 minus C of 12 divided by 0.001. And we say, well, the cost function doesn't exist at 12.001. It's defined at 11, it's defined at 12, it's defined at 13. It's not defined at 12.001. So we're taking this limit, but the closest H can get to 0 is 1. When we try to let h be less than 1, when we try to let h be 0.001, we ran into a problem. On the other hand, h can be 1. If h is 1, we get c of 13 minus c of 12, all divided by 13 minus 12. So because we're letting h be go to 0, but in real world terms, h can't be less than 1, we say that c prime of 12 is approximately, we write a squiggly equal sign for approximately, c prime of 12 is approximately c of 13 minus c of 12 all divided by 13 minus 12. And of course, dividing by 1 doesn't do anything. So c prime of 12 is approximately c of 13 minus c of 12, which is the cost to produce a 13th unit if we have already produced 12 units. And in this context, we call the derivative of the cost function the marginal cost. So if c of x is the cost to produce x units, c prime of x is approximately the additional cost of producing one more unit. And I already said this out loud, but this is an approximation. It's not exact. So let's make up a cost function and try to see an example. So here's sort of what we're envisioning with all of this. We are I'm sorry, I have this polynomial. I mean, the details aren't super important, but c of x equals 0.002x cubed minus 0.3x squared plus 15x plus 250. And the situation we're envisioning is that we are currently manufacturing 12 units. So we are currently accruing a cost. And this is just algebra. If we take 12 and plug it into this polynomial, we get 390.256. And now we're thinking about expanding. So we ask a question. How much additional money would it cost to manufacture a 13th unit? And this is approximately C prime of 12. So to find C prime of 12, we have to find C prime of x first and then plug 12 in. So C prime of x. All right. We're adding and subtracting stuff. So we just take these derivatives of the things we're adding and subtracting, and we add and subtract the derivatives. So the derivative of 0.002x cubed. This is the power rule. The 3 comes down, and then the 3 is reduced by 1. So the 0.002, that's a constant. It just sits there. So when the 3 comes down, 3 times 0.002, 0.006 x squared. The power is reduced by 1 according to the power rule. Minus the 2 comes down, it gets multiplied by 0.3 minus 0.6x. The derivative of a constant times an x is the constant. The derivative of 15x is 15. The derivative of a constant is 0. The derivative of 250 is 0. So if we want to know how much additional money it would cost to manufacture a 13th unit, be careful we don't stick 13 into the C prime. We stick 12 in there. And C prime of 12, I just did this off screen, as it were. C prime of 12 is 8.664. And this is an approximation. And in this specific case, because we have the cost function, we can check our work, as it were. I mean, we're not exactly checking it because we know it's an approximation. We don't expect to get this number exactly. But C of 15 minus C of 12 is 8.664. 0.438. So quite close to this number that we have. And marginal analysis, this kind of analysis, is extremely powerful. I introduced this in terms of marginal cost. But if R of X is a revenue function, we can just as well talk about the marginal revenue. The additional revenue generated by manufacturing one more unit. And then once you have these formulas, of course, you can ask questions, should you manufacture a 13th unit? Well, manufacturing a 13th unit will create additional cost, C prime of 12, and it will create additional revenue, R prime of 12. Should you manufacture an additional unit? Well, you would want the additional revenue you get to be greater than the additional cost you accrue. So you'd want R prime of 12 to be greater than than C prime of 12. Sorry about that. So profit as well. You can talk about marginal profit. And again, this is kind of the canonical example. We'll see other applications of calculus to business. We'll talk about storage costs. We'll talk at the end of the class, we'll talk a little about areas and income inequalities and all sorts of things. But this is the famous one, marginal analysis.